Hello everyone, in person and online. My name is Maxence Menton. I am PhD from the University of Amsterdam. And today, right now, we have two presentations about the future of the Greenland ice sheet. And we'll start with Mark Series, who is director of the National Snow and Ice Data Center in Colorado. And he will give us a perspective from observational records on the future of the Greenland ice sheet. And we'll have the Q&A after the two presentations that we have today. Thank you very much.
Well, greetings, fellow citizens. We're going to talk about the Greenland ice sheet. We've talked about the Greenland ice sheet quite a bit already, but we are going to continue to talk about the Greenland ice sheet for a while because it is so important to the future of our planet. So as I've said, I'm Mark Serez. I'm with the National Snow and Ice Data Center, the director there. There's also a Twyla Moon, who's one of our scientists, and she's our Greenland expert, or one of them. Now, there we are. All right. Now, we've talked about glaciers. We've talked about Greenland. And this map is showing in the blue where, of course, the world's glaciers and ice caps are. Some of you here may remember of the issue with tropical glaciers, that they are destined to be gone very soon, right? There's not many of them. They're small, but they're destined to be gone. And we've had, of course, we know what's happening to glaciers and ice caps, like in Greenland, over the Canadian Arctic archipelago. But again, now let's focus on Greenland, which I'm showing here. Now, the first thing just to get at Greenland is how big is it, or how tall is it, right? It's something like 6 meters of water equivalent, depends, I guess, on how you figure it. But it's about 3,200 feet high at the center. So what Twyla did is she put this all in stacking up statues of liberty, right? That American democratic icon there to show how high that Greenland ice sheet is. Now, when we're talking about the mass loss of Greenland ice sheet, of course, I think we all know that Greenland is losing mass. We're talking about it in terms of gigatons, right? Gigatons is a lot of tons, right? 1 followed by 9 zeros is basically a cubic kilometer of water. Think about a cubic kilometer of water. That's a hell of a lot of water, right, that we're talking about in terms of a gigaton. Now, what I'm showing here is a record of the total mass balance of the Greenland ice sheet going through time. This is based on data from an instrument known as the GRACE instrument, gravimetric. It's very clever. It's got one satellite in front of the other, and they're separated by a certain distance. And when one goes over a gravitational anomaly, the front one, let's say a positive gravitational anomaly, it speeds up, because, of course, orbit is a free fall. Well, then the other satellite behind it sees that gravitational anomaly, and that would speed up or slow down, whether it's a positive or negative gravitational anomaly. And by looking at just the changing distance between these satellites in a very clever way, one can determine changes in the mass that is flying over through time. Now, just going, you see those ups and downs year to year. What you're seeing, there's a couple of different effects. The downward trend is, of course, the downward trend in the total mass balance. But you see these ups and downs on a seasonal basis. A big part of what you're seeing there is what we call the effects of the surface mass balance. That is the accumulation that you get every year, primarily from snow, minus the summer melt. And of course, there's a strong seasonality to that as well. So that surface mass balance goes down in the summer, goes up through the autumn and the winter. But of course, there's this overall trend. And it's a relationship between what's happening to the surface mass balance and also the dynamic mass balance, which is really relating to the discharge of icebergs into the Atlantic on one side, or to Baffin Bay on the other side, one of those which certainly sank the Titanic many years ago. This is just another view of of the mass balance, total mass balance of the Greenland ice sheet compared to the Antarctic ice sheet and the two total. This particular analysis only goes through 2012, but it gives you the idea, and something that's been talked about before, that of our planet's two ice sheets, and of course we only have two, the Greenland ice sheet and the Antarctic ice sheet, it's the Greenland ice sheet that is really making the move now. That's the one that we're really losing the mass from. The Antarctic ice sheet, yes, somewhat downward, but the Greenland ice sheet is certainly leading the way. Now, this, of course, has many effects. We, of course, know all about the sea level issue. We've talked about sea level a lot. Greenland's a major contributor to sea level, and that contribution seems to be increasing. We talked about it particularly, certainly out in the future, what it's going to be, but already now in terms of storm surges and how even a modest rise in sea level can have a big effect when we start to combine that with storm surges and things like that. But also there's other effects, because as we melt down the Greenland ice sheet, what happens is that we put fresh water on the top of the surface, and that can actually start to affect things like ocean currents. Now, we look at here, like in Glasgow, you have this wonderful mild climate here, right? Beautiful, wonderful, mild climate. Doesn't really get below freezing much in the winter. And that's because of this conveyor of fairly warm water that's coming down from the south that's moving up north. Part of what we call the North Atlantic Drift. It loses its heat to the atmosphere. Of course, that warms it up here in Glasgow. Eventually, that water sinks in certain areas, like in the Greenland Sea, and then returns to the south. So thinking there is, if we really put a bunch of fresh water on the top of the Arctic Ocean, or here in the North and North Atlantic from Greenland, can we influence that? Can we influence that circulation of the ocean? And that's a very important issue, not just because of climate, because that could affect like the climate of Glasgow right here, but of course things like fisheries, okay? Because that could also have an effect. We change ocean currents, we change the conditions, we could change fisheries. So in other words, this could have large effects on climate like of Northern Europe, but certainly some direct effects also on economies, such as within this very region. Now, in terms of what's happening to the ice sheet, in terms of its mass balance, as I mentioned, there's two things going on. There's this surface mass balance. That's the difference between the accumulation that you get primarily through snow, and then the summer melt and the summer runoff that we get. There's also a sort of a piece of sublimation or evaporation in there, which is fairly small. There's that piece of it. And we know that that surface melt is starting to increase. And some years it's been quite extreme. This is just an example of a meltwater stream. This is going to be something down fairly low in the ice sheet, what we call the ablation zone, at the lower, warmer elevations. And here we have meltwater disappearing to, it looks like a moulin. Right? I've understood that maybe Georg could correct me with this, a number of grad students that have been lost through the years through these things. Perhaps so. I don't know. But this is, what happens here. You don't want to slip and fall into one of these things. Right? But there's a lot of things going on that can increase that melt. Now, of course, the climate's simply warming up. We know that, right? As someone said many times, you can't argue with the melting point of ice, right? A warmer climate, more summer melt. But there's various feedbacks, because as we start to melt, we start to darken the surface. That is, we lower what is called its albedo, which is simply the reflectivity in the wavelengths of solar radiation. Well, if we decrease the reflectivity, of course, we absorb more solar radiation, and so that certainly just simply increases the melt. And of course, we're observing that. What you see here also on the top right is those little blue specks. Those are melt pots. Okay? Those actually bear into the changes in the dynamical mass balance, which I'll talk about in a minute. There's biological processes that can decrease the albedo, but a lot of it is just melt. Right? As you get the melt going, you drop the albedo, and there you go with the feedback. Now, let's talk about the dynamics, right? The dynamics going. We talked about that surface mass balance. We'll talk about the dynamics, which we're really talking about here is the discharge of icebergs. Now, one of the most important things here about Greenland ice sheet and these icebergs that are produced is that we have a lot of what we call marine terminating glaciers. Now, these are immense glaciers, huge glaciers, which terminate in the ocean. And of course, they discharge icebergs as a result, like probably the one that sank the Titanic. It's pretty safe to assume it probably came from Greenland. And they act really as conveyor belts, okay, because they're conveying ice from the ice sheet, okay, out of the ice sheet and into the ocean. They're really conveying, they're basically, think of it as they are what is draining the ice sheet in terms of the ice itself. Of course, there's also melt going on. But they are really these conveyors. And what I'm showing here, I'm not sure if it looks like the animation's not working here, but that's okay. But there's vectors here that we're showing the flow of that ice. And as we get near the terminus, that flow speeds up. Now, the ice dynamics, these are key. These are key to the mass balance of the ice sheet because of these conveyor effects. There's some really, really big ones like Jakobshavn, the Petermann Glacier, and there's others. And this discharge of icebergs is very, very large. Okay? Overall, we find that in general, what we've seen, if you had a stable ice sheet, you'd have the dynamic balance, which is always negative. In other words, it's always dumping mass out of the ice sheet through icebergs, but that would be balanced, okay, by this, what we call the surface mass balance, which would be positive then, and the two would be in balance. Well, that's not happening anymore, right? We're changing both the surface mass balance and we are changing the dynamical mass balance as well. Now, there's a lot of feedbacks and things happening, okay? What we're seeing is a lot of these glaciers, okay, that are draining the ice sheet are speeding up, okay? They're accelerating. They're moving faster than they used to, right? There's a number of processes going on here. I mentioned those melt ponds, okay? One of the things that people have looked about is how these melt ponds can catastrophically or very quickly drain to the bottom of these glaciers that drain the ice sheet, something that had been called popularly the Zwally effect, because popularized by a NASA scientist, Jay Zwally, although it's been known for some time, really. What they call a basal lubrication basically actually lubricates the bottom of the ice of the glacier. So that's one thing. But there's also a lot of things going on which are viewed to be more important, I believe, right now, such as back pressure effects. Okay? The glaciers are thinning, which means things like the fjord walls and things like that, or under ocean sills, which would tend to buttress that draining glacier and keep it from moving fast. As the glacier thins, that back pressure effect becomes less. There's less contact of the ice with the fjord wall. You could be lifting above these ocean sills. And so then the glacier can now move faster. And there's strong ocean effects on that, causing that. We've already talked about them a bit for the Antarctic ice sheet. Similar effects are occurring here. But also as we thin it, okay, that, of course, we flow the ice faster, but there's feedbacks in that the accelerated flow also induces thinning and iceberg discharge. So the point is there's a number of processes and feedback effects that accelerate these changes in the mass balance of the ice sheet. Topography is important. Every glacier is different. Every glacier, the fjords are different. The bedrock sills at the bottom are different. The internal drainage of all of these different glaciers all could be very different. And so it paints a very, very complicated picture. So in other words, I talked about some of these things, the thinning effect, this basal lubrication, all of these things. These are all occurring, but very, very much dependent on the particular glacier and the topography, the fjord. All these things interact, which makes it a particularly difficult nut to crack when we start to want to make projections of what's happening in the future. And so, again, I'm not sure. It looks like these animations aren't quite working here. That's okay. But again, this ice loss is happening. It's speeding up. Right? If we want to really keep that sea level down, right, to something that is manageable, the sea level rise down to something that is manageable. Oh, it looks like it is going now. Well, who knows why, right? Any case, this is just showing a bit of a simulation. This is a simulation. This is just a teaser for our next talk coming up about the thinning and the speeding up of these glaciers as we move through time in a warmer and warmer climate. And this is going through quite a bit of time here, but big changes to the ice sheet and the size of the ice sheet. And of course, this is contributing to sea level. So with that, I'm going to stop and I'm going to pass the podium to Julie Brigham-Gretty, who I believe is in our audience. I certainly hope so. So, thank you very much.
Okay, thanks, Mark. That's a perfect segue into just a few more points that I'd like to add to this discussion about the future of the Greenland ice sheet. When I was a graduate student, I was taught that the Greenland ice sheet was stable, but we now know that that may not be the case. And so maybe Greenland's future is actually to become green again. That may be where we're headed. So one of the fantastic things that's come out of this science program, particularly through NASA, is reconstructions of what the topography under the Greenland ice sheet looks like. And what we now know is that, in fact, Greenland, if you take the ice away, it's a basin. So this means that all of these glaciers around the margin that Mark just talked about are draining into a basin. And so, in fact, the ice sheet is getting thicker and steeper faced as the ice retreats inland. So there's nothing in the way to stop many of these major outlet systems from retreating back into the very core of the Greenland continent. And this is very important in trying to understand what could possibly be pinning points that might stabilize the ice sheet possibly in the future. So Mark just showed you an animation from this paper that came out recently. And I think you need to take a hard look at this paper. The top 4 panels show you left is the observed on A, and then B, C, and D are the 2 RCP scenarios, 2.6, 4.5, and 8.5. And the bottom 4 panels are the velocity or speed of the ice that Mark just showed in that animation that you saw. And each panel is showing you what the ice sheet might look like by the year 3000. That's not 3,000 years from now, by the year 3000. So that's, a little less than 1,000 years from now. You might think that the demise of an ice sheet might take many thousands of years. But the suggestion here is that, in fact, Greenland is actually quite vulnerable to very relatively rapid on geologic timescales of disintegration, particularly in the high emissions scenario, which we hope we don't achieve. But I think it's important to think about the fact that it may not take as long as we thought, and that even by 2100, this ice sheet may contribute as much as 5 to 30, over 30 centimeters of sea level rise just within the next 80 years, which again isn't very far away. This figure is also in the same paper, and in the columns, the low emissions, medium emissions, and high emissions simply show the melt rates. So the more orange and pinks you see, the more melt you see. And you notice that here at the very end in the 8.5 scenario, the melt that decreases. Well, that's because the ice sheet's so small, it's gone. So the melt rate is really low. So you see a large jump once we get beyond essentially present temperatures for the most part. So let's think about Greenland for a minute. How old is the ice there? This is an ice animation any of you can look at on the NASA website, on their visualization website. And it shows, based on many ice cores through the ice sheet, kind of a simple diagram showing you the age of the ice as you get down deeper into the ice sheet. And we know probably somewhere in the base of the ice sheet, there's ice that probably survived a little bit of the last interglacial 125,000 years ago, when the Earth was about as warm as today, or about 1 degree warmer than now. But much of that ice sheet is actually quite young. So it begs the question, wait a minute, how if Greenland is kind of stable, why isn't there more older ice there? So did the ice sheet disappear? When did it disappear and how often? How can it disappear? So a study came out a couple of years ago by Schaefer et al. In 2016. And what they showed was the results of the accumulation of cosmogenic isotopes that accumulated in the rock under where we took the ice cores. So where the science community collected the ice cores, they collected the ice, and then they went into the rock below. And you could take that rock and analyze it for beryllium and aluminum and for cosmogenically radiated isotopes that are from cosmic ray bombardment. And this bombardment, if you know the rate and when, you can tell how long it's been exposed. In this case, we can only measure the accumulated beryllium and aluminum. And then we had this Goldilocks scenario, like, okay, what led to that? Was it the top one, number one? Here, I'll go to the next one. Number one, is it a long period of exposure and then ice cover? Number two, was the Greenland ice sheet gone on a regular cycle? Or was it more complicated than that? That there were periods when Greenland was gone, periods when Greenland came back? And how does that compare to the climate sequence? So that's a compelling question. When did Greenland disappear and how often did it disappear? So to answer that question, one of my grad students, Benjamin Kiesling, worked on with me, many scientists. We drilled this lake in northeast Russia. It's a meteorite impact lake that was created 3.6 million years ago. And in the sediments there, we were able to collect a continuous sediment record of the Arctic for that entire period of time. It's a phenomenal record, nothing like it anywhere else, because that meteorite hit in one of the few places in the north that was never glaciated by continental scale glaciation. So we've looked and used that climate record from the last 3 million years to then drive a history of the Greenland ice sheet to see what happens. So what you see here, this is, Benjamin hasn't published this yet, by the way. On the left, you see the model ice sheet, the climate model and ice sheet model synchronization, showing using the Elgagikin climate scenario to drive the waxing and waning of the ice sheet. And you can see that it comes and goes over the last 2.5 million years. At the same time, whenever the ice sheet retracts, he bombards the land, the rock, with cosmic rays to then accumulate and see if he can match the measured accumulation of isotopes in the rock versus the ice sheet history. So you see where I'm going? And so what he came up with is, in fact, two scenarios that he can't eliminate. Using that history, he comes up with these two histories. So the pink bands are when the Greenland ice sheet disappeared. The blue bands are when it came back. And so what this shows you is that, in fact, the Goldilocks scenarios, scenario 3 is probably most accurate. That, in fact, the Greenland ice sheet has disappeared many, many times. And particularly even in the last million years, it's disintegrated several times. And there's lots of field evidence showing that, in fact, the Greenland ice sheet had to have disappeared, particularly at about 400,000 years ago, is an agreement. So the story here, which is that the Greenland is, in fact, much more vulnerable to collapse in it, even from natural climate cycles. Very small changes in temperature can drive this ice sheet to disappear. So that's a really important lesson here. Now, to test this idea, the International Ocean Drilling Program has 2 pending proposals to drill offshore of northeast Greenland, and I think it's northwest Greenland, to explore in the continental shelves off Greenland this scenario, and to see, in fact, how we can refine our history of how true, how accurate is this this idea that the ice sheet came and went many, many times. And this paper at least suggests that, yes, once it gets going with a warm world, it can disintegrate quickly. In fact, some models suggest that particularly once we start to get more summer sea ice in the Arctic, so there's no sea ice in the summer, which is forecast to happen by 2040, 2050, no ice around Greenland in the summer, this ice sheet is really going to go quickly. That's a really big game changer. So the answer here today is, okay, what we're all here in Glasgow for is to keep the world cooler, keep us below 1.5 degrees, because the consequences of a warmer world are certainly a threat to these large ice sheet systems. So the truth is, the future of Greenland may be to become green again. Thank you very much.
Thank you very much. So now we'll take the questions for both presentations. You're welcome to ask them here. All right.
I'm sure I can start speaking while he's coming up. So yeah. Krista, University of Colorado. Hi, Mark. Is most mass loss currently taking place in Greenland coming from, I forget the calving, or from melting?
Yeah. My understanding, and Julie could correct me if I'm wrong here, is that both the dynamic mass loss and the surface mass balance are highly variable things. Okay? And the question is, which will become more dominant? Okay, as we move to the future, is still a bit of an open-ended question. Now, historically, of course, the surface mass balance has been positive, and that, of course, balances the negative mass balance part from the dynamical component. But we're seeing in recent years a number of years in which the surface mass balance itself, over an annual cycle, appears to have gone negative, right? And so that is really kind of disturbing, but we'll see if that lasts. Julie, correct me if you need to, please.
My impression is that the melt rate is really rapid, and so that the surface melt at the moment is higher than the calving rate from the margin, because you're melting around the entire margin, whereas the calving is only happening in certain locations.
Yeah. I asked in part because, Mark, you seem to, in your presentation, you seem to fixate just on calving from glaciers and flow rates of glaciers.
Oh, no. I should have probably added more slides. Now, the problem is to get the surface mass balance, to know it, okay, is not easy to do. Same thing with the dynamical mass balance, because we can measure surface melt at particular locations, just like we can look at glacier flow at particular locations. But to understand the surface mass balance, you need to know what's going on over the entire ice sheet. And that is very, very difficult, okay? Where most work has been done is actually from a modeling approach, where you take something like a melt model, a very robust melt model, and you drive it with output from what we call an atmospheric reanalysis, basically a weather model, okay? And so that's how you see what is going on. Now, that's a model, right? You know, all models are wrong. Some are useful, right? But it that was George E.P. Box, I believe, who said that, right? but it's very tough to even get really accurate numbers. But from what I understand, yeah, the surface mass balance is if it's still positive in some years, but it is definitely becoming negative.
Right. The melt rates have been tremendous, and this is why part of that surface melt is also being accentuated by black carbon that's accumulating on the surface. That's why there's a big push in the Arctic Council about trying to eliminate black carbon and soot from getting to the ice sheets. So that's accelerating the melting. It's kind of second to temperature. But the surface melt has been tremendous. These moulins are delivering that water to the base of the ice sheet, lubricating parts of that ice sheet, even on a seasonal basis.
Just one thing to add on the total mass balance is something we can get at, okay? Because we have GRACE, okay? I mentioned that GRACE instrument. GRACE died, satellites dies, but now the new GRACE instrument came on because it was seen to be so successful. So we can actually get from GRACE a pretty good idea of what's happening to the total mass balance. The tough thing is splitting it into the two pieces.
So just to make sure I'm totally clear, there's some uncertainty. I get that. And there's a lot of surface mass balance, a loss from surface melt. But right now, surface melt is presumed to be more than loss from calving. And in the future, is that expected to be even more so the case? That's all I have.
Yeah, it is. And I believe I have it right. Eric Renaud and others put out a paper where they took each of the various sections of the Greenland ice sheet and have mapped its melt rate. And so that's a really good paper to look at for each of the sections of the Greenland ice sheet. You guys agree? Yeah. Okay.
Good.
Hi. Fascinating to see the images about the bottom, the surface of Greenland. I'm just wondering if the land is bouncing back. I think you guys call it isotopic rebound.
Isostatic.
Isostatic.
Yeah.
Sorry, I'm not a scientist. I got it, part of it right. Wouldn't that have an impact if where the ice will go into as far as the basin is concerned? Because you're saying it's now going into the middle of the land.
I can go back.
Yeah, Julie knows her geology, so I'll leave that one to her.
I think it's fascinating because it would have an impact of what will happen to the glaciers on the extremities, right?
Yes. So the glaciers that are following valleys that go back into the center, they're not trivial. They're large and there are many. Particularly in the northeast Greenland, there's a gigantic area. It doesn't quite show up on this particular image, but they call it the Grand Canyon of the Greenland ice sheet that's underneath there.
Right.
There's a tremendous amount of access from all sides back into that interior basin. So in all simulations, the ice always retreats from this area, and then the last bit of ice is always hung up on these mountains on the east side.
Right.
And so that's kind of in all of these future scenarios. And it's interesting, as a geologist, I mean, we know off in the North Atlantic here, there's ice rafted debris from Greenland as early as 8 million years ago.
Wow.
So before there was really an ice sheet. So think of this side of Greenland looking like Southeast Alaska today, where you have kind of temperate glaciers calving into the sea because the mountains are high enough. But to get a big ice sheet like that took the Earth to cool a while, but that's in fact where it retreats to in a warmer world.
Mm-hmm.
But I think it's very clear that many of the sections of Greenland are actually have access right into the center of the basin.
Right. And then the rest of it will drain, but still in the ocean before you get to this point.
Right.
Yeah.
So that you're right. There's going to be isostatic rebound, but many of these systems are going into deeper terrain. So even though it's lifting up, it's not necessarily going to stop the retreat.
Right.
My understanding, Julie, is that there's some parts around Greenland where local sea level is actually falling because of the ongoing isostatic rebound. So global sea level is going up, but locally the sea level could be going down because of the rebound from the last ice age, right?
Right. Yeah. Sea level's going, and yes, in fact, there's an NSF program for navigating the New Arctic, which is monitoring that on the west coast of Greenland for the communities living there who are seeing their communities lifting out of the sea in response to that.
Well, final question then. Would it have any impact as to try to model how much the sea level will rise eventually if the Greenland ice cap will melt completely?
So the Greenland ice sheet has, most people use a number of 7 meters of water equivalent. And we think the best round number people are using now for, say, 125,000 years ago was about 2 to 3 meters of sea level. So not quite a third of the Greenland ice sheet was gone when we had 1 degree warming. So we're already baked into 1 degree. Now we're at 1.2 or 1.4 of global warming. So we know that ice sheet is bound to lose in the coming decades, centuries. It's going to lose at least probably on the order of 2 meters, 3 meters. So it's on its way. Yeah.
Yes, okay. Thanks.
Yeah.
Thank you very much for your presentation. I'm Charles Archibald, University of London, and I'm delighted to hear you talk about the truth of the matter, which is that it's accelerating, and that message needs to get out there more because people, I mean, there's a general view that it's not a problem. It is a problem. I want to ask you about the color of the ice. Is the color, because of the albedo effect that you mentioned, is the color of the ice changing either because of air pollution or because of growth, so that we might be have a change in the albedo effect?
Well, the what's it called? Dark ice, or the Jason Box group has been monitoring the accumulation of this black carbon and soot. Can be a combination of silt and industrial soot that's landing on the ice sheet. So as the surface melts, it accumulates on the surface and gets even darker. And so that is, if you can think of a little dark layer about this thick, it's actually like this warm blanket that's then accelerating the melt. And Jason Box has a big project looking at that. There's a lot of information on the web, but that's actually a very serious problem for not only the Greenland ice sheet, but for sea ice and any white bodies.
But I was thinking of the reflection of the sun.
Yeah.
And are we tracking that? And also, I understood there was some growth that was on certain ice sheets that is reducing the albedo effect.
Well, in terms of monitoring the albedo, oh yes, we can do that by satellite.
Right.
We have the moderate resolution imaging spectroradiometer and other satellite systems, and can monitor the albedo, and we in fact do that, right? And you see that the albedo has a strong seasonal cycle. It gets to a minimum in midsummer, then goes up again. But the albedo appears to be dropping because of the melt. And the thing is, all of these things we look at, the albedo effect just from melt, the accumulation of the dark particles, the thinning of the ice sheets, all of these things point to or contribute to acceleration of the loss. It is not linear.
Right. So the net point is that the albedo is decreasing. There's less reflectivity across larger portions of the ice sheet because of all these processes, to answer your question.
Now, of course, regular glacial ice is a nice blue color, right? It's actually beautiful if you go up there and look at it, but that's a different issue.
Yeah. Any other questions? Anything online? Okay. Okay, we have one in the back.
Hi. Hello. Just concerned citizen, really.
Okay.
Good to be concerned.
Yes.
Oh, can you get that one up?
Yes. Well,
So,
Yeah.
yeah, that one. So I just want to ask, so if we hit RCP 2.6 by the end of this century, what's the average sea level rise around the world?
Well, so we're at about 1 degree, 1.2 right now.
Yeah.
If we could just hold right there,
Uh-huh.
the future would be long term would be 6 to 9 meters of sea level.
6 to 9.
6 to 9,
Right.
because basically, and we know at least that would be an outside, because that's what we were. The world was about 1 degree warmer than now, 125,000 years ago, when we think this ice sheet was contributing 2 to 3 meters of sea level,
Mhm.
and the rest of it may have been coming from West Antarctica.
Okay.
And so there are many studies, and said Max, who did the introduction, trying to get what did the West Antarctic ice sheet look like in the last interglacial, try to get that as right as possible, and also understanding this to accommodate, here's how much sea level rise we see, where did it come from, and get that right, because that's kind of where we're headed right now. That's already baked in. And I think what's really important for general citizens to understand is that these ice sheets are lagging behind the climate of the day. So what Greenland is doing now is responding to what happened decades ago.
Yeah.
So in the future, it's going to be catching up to today. So there's this because of the sluggishness in the system, in the glaciology of the system, these ice sheets take a long time for that margin to respond. So we've already baked in, so to speak, a lot of change in both ice sheets.
Yeah. And I think what some of Julie's work's showing is that the importance of paleoclimate research, right, to understand the past, because if we're going to understand the present or where we're going, we have to understand what happened in the past to get that context. So that's why paleoclimate research is so critical.
Yeah, and let me just add that these previous warm periods were not driven by CO2 necessarily. They're driven by changes in the Earth's orbit and the shape of the Earth's orbit around the sun, which changes insulation. But that mimics the CO2. What the CO2 is doing is forcing the climate just the same way Milankovitch orbital changes on long, tens of thousand year time scales does. So we can use those natural experiments to then look at the different forcings and see what the forcing from CO2 and methane is that mimics these previous times.
And to those skeptics out there who say this is all some kind of a natural cycle, okay, that does not absolve you from the responsibility of finding the cause, right? Climate change doesn't happen all by itself. There's no Harry Potter that can flick a magic wand. You identify the forcing, we know the forcing today.
As humans.
Thank you. Very worrying.
Yes, very worrying, for sure. Any other questions?
I guess we're out.
If not, in a little while, we're going to talk about both ice sheets, a little bit about both the tale of two ice sheets. So that's coming up later today. Thank you for coming, and enjoy the rest of your day.